Okay, so in this video, we're going to again talk about adding and subtracting vectors and multiplying vectors by scalars, but this time we're going to do it more mathematically by defining something called vector components. Okay, so let's first just remind ourselves what we learned in the last video about adding vectors. If I want to add together a plus b, I take the tail of b and I place it on the head of a, and then I draw my resultant vector in, a vector that starts at the tail of a and points to the head of b. Okay, so this is a plus b. Or I could do b plus a. This time I take the tail of a, I place it on the head of b, and I again draw in my resultant vector as being a vector that starts where I started, at the tail of b, and that points to the head of a. Okay, so again, I'm sorry, this is b plus a. Okay, and as we saw, a plus b is equal to b plus a. Okay, so let's now define vector components. Okay, well, just a little bit more about vectors. So first off, let's now start drawing the vectors on a Cartesian coordinate system, on a normal xy coordinate system with a typical grid, right, where we have, 1, 2, 3, 4. In the plus x direction, we have 1, 2, 3, 4, 5, 6 in the y direction, etc. So we can draw our vectors on this grid. And as a reminder, for a 2D vector, right, a vector in two-dimensional space, so a vector that's in the x and the y direction, we need two pieces of information to describe this vector mathematically, right? So far we've done things like saying, okay, this vector is 4 units east, or I walked 7 miles north. Now we're going to do it a little bit more mathematically, right? Here we can use the components of this vector to describe it mathematically, okay? So let's do that. And let me just make the point here that this vector is totally the same as this vector. So I can draw this vector anywhere, right? And it's totally equivalent, right? It doesn't matter where I draw it. I can move it around. These are all A, okay? They all are still the same vector. They have the same direction and the same magnitude. Okay, so let's now define our vector using what we will call vector components. So I can recognize that this vector I could describe as having 3 units along the x direction and 4 units along the y direction. Okay, so I need 2 pieces of information to describe this vector. That seems like 2 good pieces of information to use. Okay, so we are going to call those vector components. This is vector A. I'm going to define the component along the x direction to be a sub x, all right, for the component of vector A along the x direction, and the 4 units here, the component of A along the y direction, to be a sub y for the component of vector A along the y direction. Okay, this is how we can describe this vector. A sub x and a sub y are not vectors; they're scalars, right? These are just numbers. But these 2 numbers in combination, if we define them in the right way, can be used to define our vector. Okay. So we're going to introduce some new notation here, and this may be a little bit different than what you've seen in math class, but it turns out this is an extremely common and relevant way to define vectors in physics, and I can explain more about why that is later. Okay, so the notation we're going to use is if I'm going to define my vector A, right, which I'm doing down here, I want to define vector A. I want to write it such that I can communicate that it has 3 units along the x direction and 4 units along the y direction. But I need to keep those separate, right? Those are 2 separate quantities that I always have to tell to you separately. Okay. So in order to tell you about the x component separately, I'm going to say a sub x, then I'm going to write down an I with a little hat symbol above it. Right? So this is something called the unit vector, which is going to indicate that something is pointing along the x direction. I specifically is going to mean pointing along the x direction, okay? Where the y component is going to be along the y direction, and we're going to use a j with a little hat above it to denote the y direction, okay? So we have 3i hat plus 4j hat. This is a vector statement where we can define our vector using what we call unit vectors. Okay, I'll explain more about what unit vectors are in a moment. Why do we do this instead of doing what you do in math class, where you may say 3, 4, or something like that to define this vector? Well, first of all, right now I'm drawing the tail of this vector such that it starts at the origin, but as I told you earlier, this vector is still 3, 4 if I draw it right here, right? It's still 3 units in x and 4 units in y, right? Which is not typically how you would draw something in math class. And separately, in physics, it's common to change coordinate systems, right? Sometimes we're going to use a Cartesian coordinate system where we have x and y. Sometimes we're going to use polar coordinate system where you're moving in a circle and it makes more sense to talk about what angle something is at. So we're going to have unit vectors in polar coordinate systems. We're going to have unit vectors in Cartesian coordinate systems. So that's why we do this in physics, why we use this certain notation. So we'll have to get used to this because you're going to see this a lot in your future. Okay, so more about unit vectors. What is a unit vector? So our unit vector I hat is a vector of length 1 pointing in the plus x direction. All right, so the unit in unit vector means it has length 1. And so I hat is a vector that always has length 1 and always points in the x direction. Okay, so that is kind of what I hat is. And I can see right here, if I have 3 I hat, that's just kind of 3 unit vectors along the I hat direction, right? We know how to do 3 scalar times a vector. It just makes this vector 3 times longer effectively, right? So when I say 3 I hat, right, that's a vector of length 3 along the plus x direction. Similarly, j hat is a vector of length 1 pointing along the plus y direction. Okay, so if I say 4 j hat, that is 4 unit vectors up along the y direction. Okay, so this is our just way of keeping things separate, right? Since I hat always points along x, j hat always points along y, I can always keep things separate and write out my vectors by saying 3 I hat. That always means that whatever is in front of the I hat is whatever is in the x direction, whatever is in front of the j hat is what is in the y direction. Okay? So let's practice this a little bit more. Here we have vector A, which we denote with 3 I hat plus 4 j hat. So what is B going to be here, right? B has, let's see, in the y direction, I'm moving in the minus direction now, and I could draw 4 unit vectors in the y direction. So this has component minus 4 I hat, right? And then it has component plus 2 j hat. Okay, so that's how we can write out this vector. And so I've done that here, minus 4 I hat plus 2 j hat. Okay, and this is a good thing just to keep practicing. Okay, and just as a reminder, if I have a unit vector I hat, and if I multiply that by minus 1, anytime you multiply a vector by minus 1, you're just making it an anti-parallel to the original vector. So you just flip that vector around. Okay. Similarly, if I have 2 times I hat, that is just making a vector twice as long. Okay. So here I have, minus 4 I hat. That means I'm moving in the minus x direction 4 steps. Okay. And again, if I move these vectors around, it still is true. I can still define them in the same way. So vector B drawn down here, it's still 4 units to the left, 4 units in the minus y direction, and 2 units in the plus x direction. So it has exactly the same vector definition. Okay. Now if I want to add together these 2 vectors, we can do it both the pictorial way we learned in the previous video. I can use the tail to head method. I can draw an A, draw the tail of B on the head of A, and then draw in my resultant vector, right, starting at the tail of A and pointing at the head of B. Okay, so that's one way I can add vectors. But now that I know about vector components, I can also add these 2 vectors together component by component. The way I'm going to do this is I'm going to add together the x components of my vector separately and my y components of my 2 vectors separately. So if I want to add A plus B, right, that's what I want to do. I take the x component of A, which is 3, I take the x component of B, which is minus 4, and I'm going to add those 2 together. So 3 plus minus 4 is minus 1, and you notice this statement is always in front of the I hat. So I'm always keeping that separate. So I end up with the x component of A plus B being minus 1, right? And that seems to be what my picture is telling me also. When I did the tail to head method, I drew in a vector that has an x component of minus 1. Okay. For the y direction, I'm going to, again, add together the y components of my 2 vectors separately and keep them separate the entire time. So the y component of A is 4, right? It's in front of the j hat. The y component of B is 2. That's in front of that j hat. So I have 4 plus 2, which is 6. And again, I'm keeping this separate the entire time by keeping it still associated with the j hat. So I end up with the y component of my final A plus B vector being 6, right? Which matches again the picture I drew with the tail to head method. So I end up with the same answer, drawing it, totally pictorially or using components. Okay, what if I had another vector in here, vector c? Vector c is pointing in the minus y direction, has no component in the x direction. So if I want to write out what is c, well, c I could write as 0 I hat because it has 0 x component, and it has minus 8 j hat, right? It has minus 8 units along the y direction, right? It points in the minus y direction. When you write a vector like this, you don't always have to write the I hat, right? Since it's component 0, you could just leave that out and just write c is equal to minus 8 j hat. Either of these statements are okay. So if you ever see me write a vector like this, c is equal to minus 8 j hat, that's implying that it has no x component, that it has 0 I hat. Okay, so let's add these two vectors together. What is a plus b plus c, right? I use the same method with components. I add all the x components separately. I do ax plus bx plus cx. So that's 3 plus minus 4 plus 0. Okay, 3 plus minus 4 plus 0 is minus 1. So when I add these vectors all together, I'm going to get a vector with x component of minus 1. Same thing for the y direction. I do ay plus by plus cy. The y components I add all together, keeping them associated with the j hat the entire time. So that's ay is 4, plus by is 2, plus cy is minus 8. So I have 4 plus 2 minus 8, or 6 minus 8, which is minus 2 j hat. So my final vector is going to be minus 1 I hat plus minus 2 j hat. I can check this. Again, I can do this with the tail to head method. I draw A, and then I move B such that the tail of B is on the head of A, and then I draw C such as the tail of C is on the head of B, and so my net vector that I end up with is a vector that starts at the tail of A and points to the head of C. So I can see from the picture that that is a vector with x component of minus 1 and y component of minus 2. Right, so my component method gave me the same answer as my picture method. So that's a really good thing to do. Do it both ways if you can, and check your answer, right? You always want to do that in physics. If you can solve it 2 different ways, do it both ways, and check your work. Okay, so we now have multiple methods we could use to describe a vector. I could describe this vector as having 3 units along x and 4 units along y, but I could also talk about the magnitude of this vector, how long is the actual vector, and the angle it's at. Either of those methods is an okay way to describe this vector. In both ways, I'm communicating 2 pieces of information. Okay, if I know the components and I want to know the magnitude, well, that's really nice because x and y are always perpendicular to each other, right? No matter what, I'm always going to have a right triangle. Right? If I always have a right triangle, I can always use the Pythagorean theorem to figure out the magnitude of a vector. Right? So in this case, I have ax being 3, ay being 4, so the square root of ax squared plus ay squared, right, is going to be the square root of 25 or equal to 5. Right? So the magnitude of this vector, the length of this vector is 5. It has a component in x direction of 3, a component in the y direction of 4, but the actual length of the vector is 5. Okay? And let me note that this makes the magnitude always positive, right? This equation, the Pythagorean theorem, is always going to give you a positive number, right? I'm squaring both of my components, so it doesn't matter if either of these components are positive or negative. I'm going to get a positive number when I figure out the magnitude. So magnitude is always positive. It's just a scalar positive number. Okay? And again, if I want to describe this vector, I could now, instead of describing it as 3 units in x, 4 units in y, I could describe it as being a vector with magnitude of 5 and talk about its angle, right? This angle here, which I'll call theta. Okay, so how do I figure out theta? Well, I can also use trig for that. Okay, in this case, say I know the components. I know the x component is 3, so that is always going to be, well, in this case, it's adjacent to the angle, right? And I know my y component is 4, right? So that's opposite my angle. So I can use trig to figure that out. I know that tangent of this angle is going to be opposite over adjacent, right? So that's going to be ay over ax, and I can solve this equation for theta, right, by doing arctan, and I can figure out that, okay, arctan of 4 divided by 3 is equal to 53 degrees. Okay, so now I can figure out the angle of this vector. And now I can talk about this vector in two ways. I could say, okay, this is a vector with x component of 3, y component of 4. I could also tell you this is a vector with magnitude of 5, right? And its direction is 53 degrees, but I have to be careful here. I have to say which angle is the 53 degree angle, right? Is it this one or is it this one, right? I need to somehow define it to be this angle in this case. So I'm going to say in words that this vector is 53 degrees as measured counterclockwise from the plus x direction, all right? We're measuring from the plus x axis, we're measuring counterclockwise. And that's the typical way we're going to do that. But you have to be careful. Occasionally you'll see a homework problem or something where it asks you to find, maybe this angle instead or something like that. And so make sure you really read the problem. Okay. What if I had done the other thing? What if I had told you this vector has a magnitude of 5 and an angle of 53 degrees? In this case, how would you find a sub x and a sub y? Right? Well, again, recognize that we always have a right triangle because x and y are perpendicular to each other. So if I want to find a sub x and a sub y, I can, again, use trig. Okay, so let's do that here. All right, we have a triangle. The adjacent to the angle in this case is a sub x. Opposite this angle is a sub y. And the hypotenuse is our magnitude a. Okay, and so I can use SOHCAHTOA, right? Sine, cosine, or tangent to figure out what these components are. And just here's our SOHCAHTOA written out, right? Sine of theta is always going to be opposite over hypotenuse. That's the SO in SOHCAHTOA. Cosine is adjacent over hypotenuse, right? So that's the ka in SOHCAHTOA. And tangent, of course, is opposite over adjacent. Right? So in this case, I have this triangle. I can always figure out this side and this side using trig. Okay. And just now that we know about components, let's also practice some of the things we've already learned, like multiplying a vector by a scalar. Right? Here we have the vector a, and we want to multiply it by 2. So we know how to do that pictorially. We just make the vector twice as long. Right? We've done that before, making the vector twice as long, and that's what it's effectively doing by multiplying it by 2. You can note that the angle doesn't change at all when you multiply a vector by a scalar, right? You're not going to change the angle, right? So 2a is always going to point in the same direction as a, okay? But let's also do this with components. If I know the vector definition of a, if I multiply this by 2, right, 2 times this vector, I'm just going to multiply 2 by 3 to get 6, and still keep that in front of the I hat. And I'm going to multiply 2 by 4, and still keep that in front of the j hat. So I end up with 6 I hat and 8 j hat, and you can see, all right, that's 6, that's my x component. This is 8, that's my y component. So 2a, using the component method, is exactly the same as what I got using the picture method. I can check what is the magnitude of 2a, right, by using, again, the Pythagorean theorem, where, again, I'm going to plug in, and I'm sorry, this is not displaying properly here. This is the square root of 6 squared plus 8 squared, right, because this side of the triangle is 6, this side of the triangle is 8, and when I do this math, I get 10. So the length of this vector is 10, the magnitude of that vector is 10, and the magnitude of our original vector a was 5, so we can see that when we do 5 times 2, we get 10. So the magnitude just gets multiplied by that scalar also. Let's practice again. Let's define this vector b again, minus 4i hat plus 2j hat, and now let's draw the vector minus 1.5 times b. Okay, so if I just want to do minus b, right, what is minus 1 times b? Well, that's just a vector that points in the opposite direction of b. Right, that's one of the original vector rules we learned in the first video. Minus a vector is always anti-parallel to the original vector. But we can check that with components. What is minus 1 times b? That's minus 1 times our vector definition of minus 4i hat plus 2j hat. So minus 1 times minus 4 is just 4. Minus 1 times 2 is minus 2. And I'm going to draw on that vector. 4 in x minus 2 in y. And this is my vector, minus b. Right, this is minus b. Okay, so we can see that the method with components gave us exactly the same thing as our rules told us. So what is minus 1.5 times b? Well, it's a vector which is pointing opposite of b because it's minus b, and it's going to be 1.5 times longer, right? It's going to be not just the length of b, it's going to be 50% longer, right? 1.5 times the length of b. And I can check that. I can do that again with pictures, or I can just do it mathematically. Minus 1.5 times 3, I multiply minus 1.5 times the x component, keep that totally separate, so I get 6 I hat minus 1.5 times 2 is minus 3 j hat. And that's what I ended up with here. A vector with x component of 6 and y component of minus 3. Okay. And what about subtraction? Again, we know how to do this with pictures and with the tail to head method. Let's do that, and then let's also do it with components. All right. To do this pictorially, I can figure out what is minus b. Minus b, I just flip b around, right? And now I can draw in, I can do a minus b is equivalent to a plus minus b, so I can just add together a plus minus b to give me, using the tail to head method, to give me a minus b. So let's do that. I get this vector here in green, right? This is a minus b in green. And let's check that with components. Right? If I do a minus b, this time I'm just going to take the x component of a and subtract the x component of b, again keeping it in front of the I hat all the time. So the x component of a is 3. That takes the x component of b, which is minus 4. So I have 3 minus minus 4, giving me 7. For the y component, I have the y component of a, which is 4, and then I subtract from that the y component of b, which is 2. So I have 4 minus 2, or 2. So I have 7 I hat plus 2 j hat. And let's check the x component of this is 7, the y component is 2. All right, so I got the same answer. This is a minus b with components or with the picture method. A few extra statements I wanted to make. So far I've just been talking about units. So when I draw this vector here, it has 3 units along x and 4 units along y. And so I could define this vector again like this. Or I could again define it by saying this is a vector with magnitude of 5 in direction 53 degrees, counterclockwise from the plus x direction. But most of the time when we use vectors, and it's not going to be just a purely mathematical vector like this, it's going to be a real physical quantity that has real units, right? So this could be a 4th vector, in which case the x component of this vector would be 3 newtons. Right? This would correspond to 3 newtons, and this would correspond to 4 newtons. Right? So this would be a force with magnitude equal to 5 newtons and direction 53 degrees counterclockwise from the plus x direction. Or this could be a velocity vector where the units would be meters per second, right? So just make sure you include those units if you're using vectors for a real physical quantity. And finally, I wanted to point out that, okay, most of the time we're going to use XY coordinate systems. We're going to be in 2 dimensions because this is an intro class and we're keeping things relatively simple. But in the real world, things are 3-dimensional, so we need to define 3-dimensional vectors. So to define a 3-dimensional vector, we're going to again have an x component, which is the I hat. We're going to have a y component for the j hat, and then for the z component, we're going to use a k hat. Right? So I'm going to have my x-axis, my y-axis, and my z-axis. My I hat is always going to point along x and have length 1. My j hat is always going to point along y and have length 1, and my k hat is always going to point along z and have length 1. Right? So if I define some random vector in this 3-dimensional space, I can always define it in terms of its x component, its y component, and its z component. And you can prove this to yourself if you want to go through the math. But it turns out that it's still pretty easy to find the magnitude of this vector. It looks a lot like the Pythagorean theorem. Okay, so to figure out the magnitude of a 3-dimensional vector, I'm going to take the square root of the x component squared plus the y component squared plus the z component squared. Right? So it'll be pretty easy to figure out that length if you need to. Okay, that's it for this video. On to the next one.